Welcome, everyone. I would like to thank you all for attending this little webinar where we're going to talk a little bit about the Apex optical analysis plugin for SOLIDWORKS. This is the result of some requests we had from some people who sat in on previous webinars when we talked about some specific functionality in Apex, where they basically asked for us to put on a demonstration that basically goes through the process of using Apex. And that's what we're going to go through today. Obviously, in an hour, we're going to go through it rather quickly, but we're going to give you an idea of the workflow of the Apex program and a lot about the capabilities and functionalities that are built into the software. Again, as I mentioned, for those of you who have been here for a few minutes already, there is a little chat icon, chat button that you have access to while you're listening. If you have some particular questions you'd like to ask, you can just type into that little chat box. And there are some people from Bro who are listening in right now, and they will try to answer you in somewhat real time. Sometimes we might have to get back to you later at the end of the presentation. I will tell you how to contact me directly if you would like to, if you have some specific questions related to what we discussed today or about the Apex program in general. So, and I noticed several of you are actually listening to this via telephone. So again, if trying to use the chat box right now is problematic, don't worry about it. There'll be contact information at the end of the presentation. Just get back to us with your questions at any time. So now let me start by talking a little bit about Apex and the four-step design process, which is typically the methodology we tend to try to convince users of this program to go through the design. And we will use this four-step process to show basically the different tools and functionalities within the software. Okay, so let's talk a little bit about the Apex program itself and exactly what Apex is. And basically, Apex is a way of joining together illumination engineering and analysis into a CAD environment. Who are we? We're Bro Research Organization, and we have been providing very accurate and very, very flexible tools that have been used in the optical and illumination design and analysis world for well over 30 years now. And of course, if you're listening to this, it's probably because as your CAD tool, you use SOLIDWORKS, and the SOLIDWORKS Corporation has developed the worldwide leader in computer-aided design software. So together, what we've done is put together, integrated, what we think is an extremely easy to use tool that allows you to design illumination systems. Okay, so let's ask a more fundamental question. Why Apex? Why another optical design, illumination design program? There are many out there. They've been there for years. As I've mentioned, Bro software has been available for more than 30 years. Why do we need a different one? Well, if we look at the world of illumination systems, illumination components, illumination systems are designed in CAD programs using CAD because they have to fit into whatever environment they are part of. Whether it's an automobile, whether it's a street lamp or any type of architectural fitting, there is much more involved with the illumination design, with the luminaire, than simply where does the light go. However, once you've designed those components and you have something that fits the form and function of the working environment, you need to verify that the energy output from that device will meet the basic needs of whatever the design is for: automobile headlamps, tail lamps, street lamps, etc. Ray tracing is the technique that we use to analyze the flow of energy. It's basically how we solve the fundamental equation of radiative transfer, but don't worry, I won't throw any double integrals at you during this presentation. Historically, typically, this has been done in a separate program, a program that does ray tracing. And the fact is, no matter how easy we tell you it is to transfer your data between the CAD program and your ray tracing program, and I will admit, here at Bro, we have other software tools, and we'll try to convince you, oh, it's really easy. Export the CAD file, hit the import button, apply all the optical properties, and there you are. And if you're that magical designer, that everything you design in CAD works properly, meets all of the functionalities required the first time, maybe that's true. But typically what you're going to have to do is bring it into your export it from your CAD program, bring it into your ray tracing program, do some ray tracing, do some analysis, define your sources, etc. You're going to do the analysis, find out you're going to need to make changes, maybe little tweaks, maybe major changes to that illumination system, at which point you're going to go back to the CAD program, modify the design, again, export, import, test, export, import, test, etc. I don't care how easy we tell you that is, you don't like it. We've been told that over and over by people for many years. So when you're talking about using Apex, there isn't an easy transfer. There's no transfer. You start SOLIDWORKS, you stay in SOLIDWORKS the entire time you do your illumination design. So now let me briefly talk about this four-step process, the design workflow for Apex. And the first step is to design and verify the geometry. And often, most of the time probably, you're going to define the basic structures, whether they be faceted reflectors, smooth reflectors, freeform optics, etc., or mechanical structures that hold things in place. You're going to be using SOLIDWORKS tools for those. But there are going to be some instances where, either because of ease of definition or because of the accuracy needed to actually represent the surface structure for things like aspheric type components, there are tools built into the Apex program to help you design those particular components. Once you've defined your geometry, turn them into optical components as appropriate by assigning the optical properties. The next step is to design and verify the sources. And within Apex, there is built in or included a very substantial light source library that has very accurate models, accurate radiometrically, accurate geometrically, for a large number of commercially available sources, filament lamps from automotive, and of course, lots and lots of LEDs. You can also create within the Apex environment your own emitter, either simple or complex, using surface or object-based geometry. You can design those to have any type of radiometric or photometric distribution that you would like. So once you've put the system together, which is defining the geometry and the sources, you'll need to trace rays. And basically, we represent the energy in our sources with rays. Each of the rays represent a certain part of the radiometric distribution of the source, and each ray represents a portion of the total energy coming from that source. The rays will leave that source and travel along their direction vectors until they interact with some item of geometry along its path. And after the rays aren't going to hit anything else, obviously the ray trace is going to stop. Step 4 is probably the reason you're interested in using software like Apex. You want to understand the behavior of your system, which is what we call perform analysis. And this will allow you to evaluate the energy distribution after the ray trace. And you can do radiometric, photometric calculations. You can look at area or angle information. Many, many other types of analysis are available, and we'll look at some of them as we proceed through this discussion. Again, when it comes to defining the geometry, you use the tools that are best for any particular component. And obviously within the SOLIDWORKS sketch tools of like the spline surfaces, planar surfaces, sometimes spherical surfaces, use extrusions, lofts, sweeps, etc. to create the basic structures in your system. But there is also an optics manager that will allow you to create components such as spherical or aspheric lenses, conic sections, and precise optical surfaces such as those defined by higher order polynomials. Again, not typically defined within a CAD environment, but because they are sometimes necessary in analyzing illumination or optical systems, the tools have been added via the Apex environment. And then once you've defined all of your geometry, Apex will create the ray trace ready models based upon all of your input. You don't have to send it to any other program. Once you've defined the basic geometry, you do need to turn it into an optical component. And you need to make sure that you have described all of the optically active components. By that, I mean all of the mechanical or optical structures within your design that it's possible for the light to interact with. So you may have added mechanical components simply because they can block some of the light path or scatter some of the light that is in the system. And again, you'll want to make sure they are designed to the appropriate level of accuracy. Then you'll need to apply optical property to each of the components. That might be something like an index of refraction, which would be simply saying it's made out of PMMA or acrylic or BK7 or whatever the appropriate optical material is. These will include the effects of dispersion, so how the properties vary with wavelength. You can also apply surface textures to components. You can also apply items like thin film coatings if they are part of your system design. The sources need to accurately represent the output from all of your illumination sources, and it's important that you, at least to some level of accuracy, represent the geometrical characteristics of the source to take into account secondary interactions. And real sources aren't point sources, so they don't behave like point sources. And Apex does have a wide variety of source models and modeling tools available to allow you to simulate virtually any incoherent sources. And ray tracing is basically the technique where we transfer the energy from the source through the optical system, allowing us to then analyze what the output distribution is. And then, of course, the analysis tools allow us to calculate whatever information is important to us, radiometric or photometric data, based upon the distribution of energy after the ray trace. We can isolate particular surfaces of interest if we want. We can isolate rays based on some particular requirement. So how much energy is between some particular angular spread, how much energy is into a particular region, where is the energy of a particular wavelength? All of those are questions you can ask during your analysis. I'm going to open up SOLIDWORKS momentarily right here. And this is what the SOLIDWORKS environment looks like. Of course, it's simply SOLIDWORKS. And I'm just going to open up for right now a new part file. Okay. Now you might have noticed, even before I opened this, on your command manager, there is a tab specific to optical geometry. And you can tell you're in Apex simply because you'll see this particular tab. But the other information you'll see right here is this item over in the Feature Manager area where you see the Apex Optics Manager. And within the Apex Optics Manager is where you have access to different libraries of information. And this is the information you will use to apply optical properties to your particular designs. So what we're going to do is walk through the four-step process. And I'm going to use a relatively simple design. In this particular case, we have a reflecting cavity. I'm going to position an LED at the base of that, trace some rays, and then we'll look at the output and do some analysis. So in terms of the four-step process, we want to design and verify the geometry using either SOLIDWORKS or Apex. In this particular case, the two pieces of geometry we need are the reflecting cavity as well as the target surface. both of those have been designed or would be designed within the SOLIDWORKS environment. So again, let's go back over here to SOLIDWORKS and let me close that for now. Okay, and what I have here is a model for my reflective cavity. And in this particular case, it's a CPC cone. And if we look at the sketch, in this particular case, what I've got is a CPC that's designed to have a 6 millimeter in diameter, 3 millimeter radial opening at the small end. And I want to take the Lambertian distribution of energy coming from an LED positioned at the small end and restrict that angular spread to the range of plus and minus 30 degrees at the output end of the cone. This CPC has been designed using equations. It's an equation-driven surface, you'll notice. What this allows me to do is if instead I want to have a cone with a 20-degree angle, come on, let me, there we go. So instead of, if I want a 20-degree angle and I update my geometry, I have a new cone. So what I've done is created a CPC structure that I can use over and over and over again simply by changing the parameters to those that are appropriate for the design I want to work on. In this particular case, I do want that 30-degree cone. Okay. So to turn this into a CPC, all I have to do is turn it into a revolved surface. So if we come over to the revolved surface, and here's my axis of revolution, and here would be my CPC. And I'll just click on OK. And there we go. And here's where I'd go to the Optics Manager. And in this particular case, what I'd want to do is turn this into a reflector. So if I just select my reflector here, and I can choose to apply a coating. And here's my coating manager. There are a lot of coatings already built into it, but you can also add your own information to define your own coatings. But in this particular case, I would just make it a perfect reflector. Okay, so that would be one of the components I'd need. And now I have not only the the proper shape for my reflector, I have also applied the optical properties that will allow me to do an energy simulation. The other piece of geometry I needed was a target. And for this particular application, I want a square target. And based on the size of my CPC and the distribution of rays coming out, what I want is a square target that's about 100 millimeters on the side. And again, it's a component I use a lot, so I simply have a little target component stored in my data files. So all I need to do is modify that and rebuild it. And now I have the appropriate size target. Speaking of that, what I'm going to do is come over here and built into or inserted into your design library when you install the Apex plugin are a series of some basic shapes you might want to use. Some of these are specific to Apex capabilities, including these ones that are based on our source, have the source annotation added to them. You shouldn't modify those, but what you'll also might find useful is you can create your own files that you use over and over again. And I find the optical parts area a useful place to store those reused components. So we have defined the two pieces of geometry, and let me minimize that. And what I'd want to do is to combine those into, one thing I didn't mention here on my CPC. Notice if I come back over here, Feature Manager, and edit my sketch. One thing I do want you to remember is that when you're designing components that you're going to be using with ray tracing, you need to make sure that you fully define your systems to make sure that things don't accidentally change in size or position. So before I created my CPC model, I did indeed have a fully defined sketch. And now what I want to do is to combine my CPC and my target into a fully defined assembly. And so you didn't have to see me go through the process of mating. I already have done that. So what we have is my CPC with a 30-degree angle and my 100-millimeter target. And I have mated them into a fully defined assembly. And now what we're ready to do is to put in our source and go on to step 2. So fundamentally, we are now done with step 1. But I also would like you to notice now that I am in an assembly, in addition to the optical geometry area within the command manager, I also have a sources, trace, analyze, design, and project settings. And we'll talk about all of these in particular as we proceed through. But what's important to understand is when you're using Apex, the Apex and plug-in to SOLIDWORKS, all of your components are SOLIDWORKS parts, possibly Apex-specific parts, but generally SOLIDWORKS parts. And within a SOLIDWORKS parts environment, you can apply media, you can apply coatings. However, when you're defining sources, doing ray tracing, analysis, design, etc., you must be in a SOLIDWORKS assembly. That's why these options were not available when I was creating my part geometry. So if you want to do ray tracing, you have to be in the assembly environment. But it is a standard SOLIDWORKS assembly file, nothing special about it. Okay, so we have our fully defined system, we have our CPC, we have our target. Now we're ready to go to step 2. And step 2 is, of course, to design and verify the source. And in this particular case, we are going to use a source from the Bro Light Source Library. So here we are, and I want to look at my geometry from that perspective. Makes it a little bit easier for me. What we're going to do is select an LED from the Light Source Library, and we're going to insert it so that the origin of the CAD file is coincident with the origin of the assembly. And in particular, the LED I'm going to use is the XLW-PWC1 for no specific purpose other than the shape and size. And we'll get into that in a little bit later. It will be inserted when we go through the process at the origin, and then we'd need to go through and mate it. So if I want to insert it, I'm going to get a little pop-up, and we'll create a new ray set. If you happen to have a ray set file from the manufacturer's website, you could instead insert that as well. If you want multiple LEDs, you can insert multiple LEDs at the same time. In this particular case, since we don't have any refracting components, I'm not worried about dispersion. I'm going to create all of my rays at one particular wavelength. But if I did want a spectral distribution, I could get that information as well, and we would get distributions of rays that follow the spectral weighting. But again, for our purposes, this will work fine. That for now. Okay, and it's hard to see, so let me change the transparency here. So there is our LED positioned inside our system so that the origin of the CAD file, of the part file, is coincident with the origin. And again, what I want to do is to properly mate this in place. So what I'll do is a simple mating here, and I've noticed that with this web tool going, my computer seems a little bit slower than normal, but just give me a moment here. And I'm going to mate it within the assembly itself. So I'll go front plane to front plane, top plane to top plane, and right plane to right plane. And there we go. And I have a fully defined system. So this would probably be a good time to do a do another save so we don't, just in case this web tool takes even more of my computer's resources. Okay. All right, so we've defined our source. We've already defined our geometry. We've created a fully defined assembly using our geometric parts. So verified our geometry simply by properly dimensioning them and fully defining them, if you will. We fully defined the position of the LED, but maybe we're interested in a little bit about what is the energy distribution. This is what we call the verification of the source. Now, if we come back up here to the Sources tab, you might have noticed before we started, these were the only icons that were active because it didn't have any sources. Now that I have an active source, I can do some analysis on the source. And I can get information like, first off, yes, I must select the source. So I've selected the source icon here within the Optics Manager, and we can look at some statistical data. And in this particular case, we see how many rays were actually generated, a little more than I asked for, but I do have my 1 unit of power at the default 0.55 micron wavelength. And I can also get information about the positional distribution, and I can also get information about the directional distribution. And since this LED is nominally Lambertian, I would expect on average the light is directed along the axis and covering all of direction cosine space. Okay, half of it approximately with angles with direction cosine less than 0.5, half with direction cosines greater than 0.5. So this looks like a reasonable representation. The other thing I might want to do is to get an idea of what that distribution looks like. So I can look at an excidence calculation. So this is sort of power per area. And we will look at it projected in the XY plane. But I'm going to click on that as well, and maybe I'll increase that just a little bit. And what we're going to see here is a mapping of the energy projected onto the XY plane. And because we have a domed source, we're going to see what looks like an excess of energy in this area, but that's only because there's a large region of space projected onto those pixels. But if I zoom on in here, these little blue dots represent where all of the rays will start. The light source library actually traces the rays through the geometry of the LED itself and then just propagates them to just outside the main body of the LED by about 5 microns. So when the rays start or are launched into your system, they're already in air, and the time and effort of the rays leaving the die inside and exiting out has already been taken care of in creating the rayset file in the first place. You only have to do that once. We can also take a look at the source's intensity distribution. So we can look at it in cosine space or in angular space. And again, what we would expect is to see light at all angles, because again, this is a relatively Lambertian, or this is, nominally Lambertian. And this is our direction cosine plot, and you can see definitely that all of direction cosine space is filled. So that's what we mean by source verification. We can use any of these tools to further analyze the source before we do any ray tracing to make sure that there were no mistakes made, in particular if you're defining your own source. There are also photometric calculations available to you as well, visual appearance calculations, but because we only created a set of one wavelength, we're not going to worry about that for now. Okay. And that takes us to step 3. And step 3 is to do the ray trace. And what the ray trace means is each of those 150,000 rays will leave the source and interact with the geometry until they stop somewhere, typically because they're either absorbed or there's nothing else for them to interact with. And again, we'll go back to Apex. And I would like to talk about, before we do the trace, just one other area, and that's what we call the project settings. And the project settings allow you to set some parameters. You can define the ambient medium, which is the medium of the world around your system. You can set how you want Fresnel effects to be calculated, reasons for terminating ray traces, splitting and scattering. And in this limited time, I don't want to go into too many details. I could spend an hour just talking about what some of these settings mean. But I do want to visualize the rays going through my system, but I don't want to look at 150,000 of them. So I'm just going to have Apex visualize about 100 of my rays. And then because I define my target to be 100 millimeters away, I'm going to trace the rays 110 millimeters after they stop. So if anything misses the target, I can see it. So what happens when I go to the Trace tab is I have a Trace Rays button. And when I click that button, each of the rays that have a starting point X, Y, and Z and a starting direction vector and energy will be propagated through the system. And again, the rays will propagate until they reach an absorbing surface or until they reach a location where the ray trace engine determines there's no other geometry that they can interact with. And let's zoom that out a little bit so you can see everything. Now, in this particular case, I define this surface as a perfect reflector. There are no refracting components. If I had had refracting components, we could have generated Fresnel effects. I could have applied a surface texture to this to represent, the scatter that we sometimes apply to surfaces. All of those could have been done, but in this simple model, we're not going to do that. So that is simply, that's all there is to step 3. We've done the ray trace. And so after the ray trace, we can see a few of the rays, about 100 of them. And again, that some of the rays might have exited the source and then just gone off into space. Some of them may have left the source and directly hit the target. Some of them might have left the source, hit the CPC one or more times, then hit the target, or hit the CPC one or more times and then miss the target. This is where we need to go to our final step, which is step 4, the analysis. Okay, so let's talk a little bit about the different types of analysis. And what analysis allows you to do is to analyze what is the energy distribution. Where is the energy? We can evaluate it radiometrically, photometrically, again, intensity, power per angle, irradiance, power per area, many other quantities as well. And this is where we would go to the Analyze tab. So if we look at the Analyze tab here, we can see, again, just like when we were looking at the source, we can get numerical data. Where are all of the rays? What's their power and what is their position and direction? We can get irradiance, power per area information, intensity, power per angle, and we can get it in direction cosine or angular space. We can also, if we had a polychromatic source or if we had dispersing components, we could do photometric type calculations as well. You'll notice that some of these tools are still grayed out. That's because they depend upon data that needs to be captured when we start doing our analysis. So for example, where are all of the rays? Now, if we rotate this around, we notice that, well, at least one ray went off into space somewhere, but how much? And where is all of the energy? Well, I'm making sure I haven't selected anything. If I don't select anything, I'm effectively selecting everything. And what I'm going to do is just look at the summary statistics. And if we look at the summary statistics here, we can see that our rays are either on the target or the last, you'll notice they say they're on the CPC. What that means is the last object they interacted with was the CPC. And you notice we only saw one of them, but we only see about 1% of the rays drawn, so that's effectively what we would expect. We wouldn't have expected to see more than 1 or 2 of those rays because statistically that wouldn't have happened. Now, I think we can all look at this and we know that this must be what is internally thought of as phase 6, but maybe in some instances you're not quite sure which particular surface it is you want to analyze based on this information. But if I come down here, I can select it and just say highlight surface, and you can clearly see visually indicated which surface it is on which that information is being provided. Now, why would I want to do that? Well, the numbers are nice, and knowing that better than 99.5% of my energy got there, again, assuming a perfectly reflecting surface. But now maybe I want to do some further analysis of this energy distribution. So by highlighting this surface, when I come up and choose to do another calculation, it will only be looking at the energy associated with any surface or surfaces that I have highlighted. So let me click on irradiance here. And you'll notice it does tell you that it's going to be on the selected surfaces. Don't worry, if you didn't do it in advance, you could do it at this point in time. But you'll also notice that it sized the analysis region based on the size of the geometry. And it's also made an assumption as to the planar projection of that surface. And in this particular case, that is the correct projection. I have a data resolution, and I'm going to use square pixels. And it remembered that I increased my data resolution slightly to 51 from the default 39. And so let's take a look at this calculation. Okay, and we can see here where all the rays hit. Not necessarily an overly useful tool most of the time, but sometimes it's interesting to look at. But I can also look at an irradiance projection in a false color plot. Now, we do see that this is statistically a little bit noisy. Not going to spend time tracing a sufficient number of rays because I only have a small amount of your time this morning. But what I can do, for example, is I can choose this irradiance information, and I can do a little bit of statistical averaging. So, just because we didn't do we should have traced a few more rays, I'm going to do a radial averaging. What that will do is average the data in radial zones, because this is effectively a radially symmetric distribution. So the pixels in each radial zone tend to have more in common with each other. So I'll just click on OK. Now, all this did was to create a new data set, and you might have noticed, I didn't mention it, but before we did the averaging, more of the visualization tools were available to us, because the visualization tools can work on this piece of information, this stored data set, which can be, by the way, exported as an Excel file if you want to do post-processing on it. But what we'll do now is take this average data set, and again, I can look at a false color distribution, or if I wanted, I could look through it at a distribution section. So what we see is a rotationally symmetric distribution of energy, as would be expected. Unfortunately, very little light is right at the center. Most of our energy, the highest power per area, is in this zone right out here, which goes from about 13 millimeters, out to here. So in this region here, this particular zone is where most of the energy is. Okay. The other piece of information we might be interested in is, because this is the CPC, we would expect the energy to be coming out now within a plus and minus 30 degree angular range. So let's again highlight that surface, and we can look at a radiant intensity calculation. And I'll have it plot out both cosine space as well as angular space. And I'll just click on OK. And if I zoom on in here to sort of the end of the data, we can see that that is close to 30 degrees, 27.67 degrees. And again, I could do some processing, do some averaging. If I come through here, what we see is, however, all of the energy is within approximately plus and minus 30 degrees. And let's take this and just do a distribution section through the XY plane through the middle. Again, we might want to do some averaging as well, but what we can see here is the CPC is definitely doing its job. It might not be the distribution we want, but it is doing the angular reduction that we expect from the CPC. So that basically is taking us through the 4 steps of the 4-step process. Okay, we have designed our geometry. We've defined, verified a source. We've done ray tracing. We've done some analysis. What comes next? Well, this is where we look at the data and say, well, okay, but that's really not what I want. Typically, we might want a more uniform distribution, or maybe more of the energy concentrated towards the center. So how would we go about doing that? What's the next step? What I'm going to do now is to look at what we call a parameter study. A parameter study allows you to vary, modify some of the design parameters in an attempt to improve the performance by evaluating the performance at particular fixed interval values of different parameters. In this particular case, what we're going to do is to adjust the position of the LED and see how that affects the energy distribution. So let's go back here, and let me go back to my model view, and let's look at it straight on like this. And here's the situation. I have this LED right at the base of my CPC, but the CPC ideally works for a Lambertian source that is right at the focus plane location. So this point right here is the focus of this parabolic section. This point right here is the focus of this parabolic section. And what we really want is a flat source, a flat LED positioned right at this location. You can see here that none of our rays are optimally positioned. But what is the best way to put that source for this particular source? Another thing that's interesting to notice, and part of the reason I chose this particular LED, is you'll notice even though this LED is smaller than the opening, all of the light is actually making it out the other end of the cone. So now let's set up a simple parameter study. And what I'm going to do is, again, simply move this LED back and forth along the axis. And I'm going to do that by changing one of my mates. Previously, I had defined a coincident mate of the front plane of the LED to the front plane of the assembly. So what I'm going to do is just cheat a little bit. And I'm going to instead change that to a distance mate. Okay, again, we're fully defined. But if I rotate around, what I'm going to do is select that dimension. Come on, let's go. Okay, so I have the dimension active. Now what I'm going to do is I'll just go to my Design tab, and I'm going to choose to do a parametric study. And what a parametric study will do is to simply allow me to define a set of parameters, in this case a single parameter, that will be varied in some number of steps, and then I can do different types of calculations to see how the performance of the system is affected. Let's show you how that works. I'm going to add a study parameter, and it knows that I had selected this particular distance. I could also do things like either dimensions or spline handles, any defined dimension within within SOLIDWORKS. Okay, and here is my variable name, and I'm going to change the name to something that makes sense to me, LED position. And you'll notice that the original value is 0. And what I'm going to do is say go from minus 1.25 to plus 1.25. Now I can either choose an increment. Okay, or a number of steps. So if I come here and choose, come on, 5 steps, it tells me that the increment is 0.625 millimeters. If I said 0.5 millimeters, it would say I needed about 6 steps. So I have a choice as to how many times I want to do it or what an increment is, and I'll leave it this way. Next thing I want to do is analyze the distribution, how much energy reaches my target, and what that distribution is. So what I'll do is I'll select my target plane, and I'm going to choose to add a goal. And you'll notice you have many different types of goals you can use based on power, intensity, irradiance, radiance, directional power, photometric or radiometric quantities. But let's start with power, the total power on the target. Okay. Then you get to define what region of that target you're interested in. You can choose the whole target window, or you can define an elliptical or a circular region. You can define a polygonal region if you wanted. So if you needed to know what a hexagonal distribution would look like, you could enter that as well. You can choose regions, you can define lines, and you can also set test points. So for those of you who are thinking about things like ECE standards, you can enter all of that type of information using the different geometry goals. But in this particular case, let's set a circle 50 millimeters in radius. Of course, centered on the origin. And then I can add this to my goals. A nominal boxcar type averaging will be done automatically simply because illumination sources are noisy. If you want to change the type of averaging, you can, but I'll leave it with the simple boxcar for now. And obviously averaging doesn't affect a total power calculation anyways. So let's just add that to the goals and close out. And it's been added. And again, this one doesn't make much sense, so I'm going to give it a name. And in this particular case, we're just going to calculate the total power. Something else I might be interested in is the spread of the energy. So again, this face is highlighted, and I'm going to add another goal. But this time, let's look at the irradiance on that surface. So let me click on OK again. And again, I know I have a circular distribution. So rather than averaging in the data at the corners, I'm just going to choose the circular spread and add that to my goals. Okay. And you'll notice here, I have that as well. So again, to make it useful for me, I'm going to do that. And you'll notice here, let me try to move this box a little bit so we can see it. Yes. So I can do a sum, I can do an average, I can do something like minimize the standard deviation. I'm just going to use the average. And this isn't an optimization, it's a simple calculation, so I'm not going to worry about targets and target weighting because Apex will simply modify this position 6 times and calculate these parameters, and in the end, it will show me what it looks like. And I'm ready to run my parametric study. You can see it shifted it all the way back, and it's tracing through the first simulation. And as a general statement, I would say you want to use a minimal but sufficient set of rays when you're doing this type of analysis. For this presentation, a small number of rays, but the idea is to show you how the software works, not to go through very, very rigorous ray tracing using many hundreds of thousands of rays to minimize the noise effects. So we're at the 4th position, which is actually the original position, or close to the original position, a little bit ahead of it. And this is the 5th system. And now the last, tracing the 6th system. Okay, so now it's done. You notice it tells me it's done. So let's take a look at what was calculated. And let me lift this up a little bit so I can see it a little better. So here are the results of the trials. And as I select them, the LED moves to that position. Okay. And here are the calculated information, the total power. And you'll notice the maximum power on the detector was when the LED was slightly offset to the back. And here are the irradiance calculations, the average irradiance. Okay. But again, what we were interested in is how was the irradiance distribution affected by shifting the LED. And just to let you know, why does the power decrease for these other options? Well, when we move the LED back here, there's going to be some energy that goes off in space, if you will, doesn't make it into the reflector. Once we move the LED well inside of the reflector, the rays that are leaving the LED at a very high angle effectively miss a bounce. So they don't get totally constricted down to the plus and minus 30 degrees, so they're going to go off at a severe angle. Well, what does the irradiance look like? Glad you asked. What I'm going to do is select all of the irradiance calculations, and I'm just going to look at a picture plot for all of them. Okay, so all of this information is stored over here in my results node. So there was my source analysis, my ray trace analysis, and now my study analysis. And we can take a look at them. Or I think, and we can obviously say, well, we like this one best, but let's give ourselves a little bit more information. So I'll just select them all and look at them all at once. And sorry for the shape, but it's a function of my monitor up here. I'm running multiple monitors, so it's a little bit confused. But we can see definitely that if what we're trying to get is a more uniform distribution across my detector surface, I need to move the LED backwards. Now, obviously, as well, I would need to now go in if that was where I wanted to be. Let's open my study up again. And I want it to be here. Obviously, I'd need to change my reflector or add a little cap to capture some of that stray energy. Have to make other changes. But what we can see is how we can use Apex to not only analyze the basic system, but we can also use Apex to design a better system. And more importantly, all of this was done without ever leaving the SOLIDWORKS environment. So I would like to thank you all for your attention. I have noticed lots of questions have been coming forth during this presentation. If you have further questions, please ask them now. I will stay online for a few more minutes to get the final questions. But if you have any questions or comments, please contact us at any of these addresses. You can also visit the BRO website as was indicated in your webinar announcement, and you can download a free 30-day trial of Apex for you to plug into your SOLIDWORKS environment and take it out for a spin. So again, thank you very much for your time. I appreciate your attention and look forward to your questions. Thank you.